Newman projections also show the different rotations around single bonded carbons, and these are alkanes and substituted alkanes. The different rotations are called conformations, and conformations are also known as rotational isomers or conformational isomers. By keeping either the front or back carbon constant and rotating the other 60 degrees clockwise, we can find all of the different conformations that a molecule have. To find them all, we can draw all rotations until we come to a total of 360 degrees. When rotating a carbon 60 degrees clockwise, each 60-degree turn will alternate between a staggered and eclipsed conformation. To draw all the conformational isomers for this example, I'm going to be keeping the back carbon constant and rotating the front carbon 60 degrees clockwise. To draw the first conformational isomer, I'm going to redraw the back carbon substituents, so I have CH3 at the top, Cl on the right, and H on the left. Now for the front carbon, it's rotating 60 degrees clockwise, so the hydrogen at the top left is going to move slightly closer to the CH3 on the back carbon. Each of the other groups are also just going to move slightly closer to the back carbon substituents. The CH3 at the top right is going to move closer to the Cl, and the CH3 at the bottom will move closer to the hydrogen on the back carbon. To make it easier to draw all of the conformations, we can just redraw the back carbon substituents because it's going to stay constant for the whole rotation. For the next rotation, I'm going to rotate 60 degrees clockwise to get to the next staggered conformation. H, that was now eclipsed with CH3, will be on the right side. The CH3 that was on the bottom right will now move to the bottom. And the CH3 that was on the bottom left will now move to the top left. I'm going to repeat this process, and each time the substituent groups are not moving too far from where they originated. We're just moving it slightly clockwise between the eclipsed and staggered. So now the CH3 at the top left is going to be eclipsing with the CH3 on the back carbon. The hydrogen will be at the bottom right, then the other CH3 will be at the bottom left. For the next 60-degree turn, the CH3 will now be at the top right, the hydrogen will be at the bottom, and the other CH3 will be at the top left. For the last eclipsing conformation, the CH3 will move closer to the top CH3 on the back carbon, the CH3 at the top right will move to the bottom right corner, and the hydrogens will be eclipsing. The next 60-degree turn will create the same conformation that we had originally. Staggered conformations have a dihedral angle of 60 degrees between the groups on the front and back carbons, and eclipsed conformations have a dihedral angle of 0 degrees between the groups on the front and back carbons. Staggered conformations can have two different types of interactions between the groups on the front and back carbons. When groups are 180 degrees apart from each other, they are anti. When groups are 60 degrees apart from each other, they are gauche. The interaction on eclipse conformations will be called the same name, eclipsed or eclipsing, and these will come from groups that are right next to each other, 0 degrees apart on the front and back carbons. We can have many different relationships in a Newman projection for anti, gauche, and eclipsing. For the staggered conformation, any groups that are 180 degrees apart from each other will be anti. So we can have the fluorine and OH group, anti, the CH3 and Cl, anti, and the H and H, anti. For gauche interactions, any groups that are 60 degrees apart in the front and back carbons can be gauche to each other. So I have F and CH3 would be gauche, the CH3 and H would be gauche, OH and H, Cl and OH, H and Cl, and H and F. The most important groups that we need to compare for gauche interactions will be larger groups other than hydrogen. Hydrogen is very small, and the amount of energy that will come from a Gauche interaction with hydrogen will be very little due to steric strain. For the eclipsing conformation, I have 3 different eclipsing groups. H and F are eclipsing, CH3 and H are eclipsing, and Cl and OH are eclipsing. These groups are so close to each other in the eclipsing interaction, they're going to have 2 different types of strain. And this strain leads to a higher energy value for eclipsing interactions and eclipse conformations. Eclipse and staggered conformations have different potential energy values due to the different types of strain that exist for each conformation. The different types of strain that can exist are torsional and steric strain. Torsional strain comes from the resistance to twisting around a bond due to electron repulsions between the bonds that are eclipsing. Torsional strain occurs when bonds have a dihedral angle of 0 degrees, so they are eclipsed, and the energy comes from the repulsions between bonding electrons in adjacent CH or CC sigma bonds. Steric strain is caused by atoms or groups being too close together in space, which leads to repulsions between their electron clouds. Steric strain occurs when large groups like CH3, Cl, or terbutyl are too close to each other in eclipsed or Gauche arrangements. The energy increases for steric strain when larger groups are closer together in the eclipsed or Gauche conformations. Once we know the different types of strain that exist for the staggered and eclipse conformations, we can organize them into the most stable and least stable conformations. Staggered conformations will have a lower potential energy than eclipse conformations because they will not experience torsional strain. Comparing anti and Gauche staggered, anti-staggered will be the most stable and lowest in energy because the groups will not have torsional strain or steric strain. Gauche staggered will be a little higher in energy and less stable than anti because the groups can have steric strain for larger groups larger than hydrogen. Eclipse conformations will be highest in potential energy due to the torsional strain experienced by all groups and steric strain that can be seen for larger groups that are larger than hydrogen. Using the conformations that we drew for a full 360-degree turn, we can analyze the different conformations to find the most stable and least stable conformations for the eclipse versus staggered Newman projections. To find the most stable conformation, we're going to look at all 3 staggered conformations because we know that staggered will be more stable than eclipsed. For each conformation, I'm going to look at all anti and Gauche interactions and write them down. The most important anti and Gauche interactions that I want to write down that will contribute the most to energy differences will be groups that are other than hydrogen. So I'm not going to focus on the groups that have hydrogen involved, and I'm just going to focus on the larger groups besides hydrogen. For the first staggered conformation, I see that I have 2 CH3 groups that are Gauche to each other. So I'm going to write Gauche CH3, CH3. I have another Gauche interaction between a CH3 and Cl, and I also have the same interaction on the other side between a CH3 and Cl. I'm going to write down that this Gauche interaction occurs twice. The only anti-interaction that I see is between a CH3 and CH3. So I'm going to write down anti-CH3, CH3. These are the most important interactions that we have for this Newman projection. To find the most stable Newman projection, I'm going to be trying to look at which conformation has the most groups that are anti and the fewest groups that are Gauche. If there are a lot of comparisons, we're going to be looking at the largest groups that are anti and the smallest groups that are Gauche to find the most stable conformation. To find the largest group, we're going to have to think about CH3 being larger than the halogens because the carbon has 3 other rotating bonds that are hydrogens, and although Cl can be larger than carbon, Cl is not going to be larger than all 3 sigma bonds coming from that CH3 group that are radiating out and rotating continuously. For the next staggered conformation, I have 2 different Gauche interactions, CH3CH3 and CH3Cl. For anti-interactions, I have a CH3CH3 and a CH3Cl as well. This Newman projection is already going to be more stable than the first because we have more anti-interactions and less Gauche interactions. For the last staggered conformation, I have 2 CH3CH3 Gauche interactions. And I also have a Gauche CH3Cl interaction. I only have 1 anti-interaction between a CH3 and Cl group. To rank these from most stable to least stable, the middle Newman projection has the most anti-interactions and will be the most stable. I'm going to give it a ranking of 1. The next staggered conformation that will be lower in energy than the other will be the first Newman projection that we have, where the anti-interaction is between the 2 largest CH3 groups. CH3 is larger than Cl, so we would like those 2 methyls to be anti to each other to avoid steric strain. The group that will be the least stable out of all 3 will be the last Newman projection due to the 2 Gauche interactions that it has between the 2 methyls. And these are the largest groups that we have on this Newman projection. Next, we're going to look at the eclipse conformations and rank them for the least stable. The least stable eclipse conformation will come from the 2 largest groups eclipsing with each other. And I'm going to focus on only the groups besides hydrogen, although eclipsing interactions will have a value for these hydrogen interactions with other groups. It's going to be easier and more effective to write down the larger group interactions to save time and avoid confusion. In the first eclipse conformation, I have a CH3Cl eclipsing. In the second Newman projection, I have a CH3CH3 eclipsing. And in the last Newman projection, I have a CH3CH3 and CH3Cl eclipsing. The Newman projection with the largest groups having the most eclipsing interactions will be the last conformation because I have the 2 largest groups, CH3CH3 eclipsing, but also a CH3Cl eclipsing, so there's going to be a lot of torsional and steric strain. Continuing the ranking from the staggered conformations, I'm going to rank this as 6 for least stable. The next least stable Newman projection will come from the middle because we have the CH3CH3s, the largest groups, still eclipsing with each other. And the next least stable will come from the first Newman projection because the CH3 and Cl are eclipsing, which will not be the largest groups eclipsing with each other. We can now take these rankings and put them into an energy profile for all of the conformations. The energy diagram for Newman projections in conformational analysis will have a dihedral angle x-axis and a relative energy y-axis. To organize these different conformations and rankings on the energy diagram, I will set up the relative energies with dots that I will connect based on the rankings in dihedral angles. A dihedral angle of 0 degrees translates to an eclipse conformation, so we will start with an eclipse Newman projection. I will start with the last eclipse conformation drawn from these conformations because this will directly rotate into the first staggered conformation that we have. The rotations will then correlate to all eclipse conformations at 0, 120, and 240 degrees, and all staggered conformations at 60, 180, and 300 degrees. If you imagine the rotations by keeping the back carbon constant and rotating the front carbon, the conformations will repeat at 0 and 360 degrees, so these will correspond to the same conformation. I'm going to start with the lowest, most stable conformation and put a dot for the lowest energy value at 180 degrees. Based on this relative energy, I'm going to gradually move my dots upwards to reflect most stable to least stable based on these rankings. The next most stable for 2 is at 60 degrees. Then 3 will be at 300 degrees. 4 will be at 120 degrees. 5 is at 240 degrees. And 0 and 360 degrees will be the same conformation, so they're going to have the same level for the dots. I'm now going to connect all dots to finish the energy diagram. If a conformation reflected the same interactions between all groups, they can have the same ranking or same value and same relative energy compared to each other.